Okay. Filters are necessary in hydraulic systems because we have to control contamination that ultimately develops in it. After all, once you put put hydraulic fluid into the circuit, the fluid is never as clean as it once was. But we have to keep the fluid within a tolerable degree of cleanliness that would be acceptable for the system. The method of filtration for hydraulic systems has progressed greatly in the last 70 or 80 years or so. If you look at some very early aircraft designs, the method of filtration was pretty crude. A good example of that would be like a B-24 bomber made by Consolidated. They had only really one filter in the entire hydraulic circuit. It was a Kuno type filter that didn't have really much of a degree of trapping contamination. But understand that that aircraft design was fairly tolerant of debris that might be in the hydraulic fluid. Today, that's not the case. Today, we have filtration systems that are much more refined, that can trap particle sizes to levels that would be unthinkable years ago. So again, as the systems become more complex, we have to kind of protect against contamination. The big thing that we're worried about in fluid would really be blockage of components from seeing hydraulic fluid. So some of the orifice openings in components are extremely small. And again, you'll block the entrance or the exit of those components with fluid, so obviously they're starved of fluid. The other thing that we have to be concerned about is the abrasive nature of some of the fluids or some of the contaminants. For example, things like sand, grit, materials like ferrous and non-ferrous metals that may cause abrasive wear inside of a component. So we're really faced with really two obstacles that we have to control. You have to prevent blockage of fluid, and you also have to prevent the passage of abrasive materials that lead to wear and tear of components. Filters are usually classified in terms of degree of filtration in three different ways. On many of the filtering elements, you find a rating that's defined as an absolute rating. There's another rating called a mean rating and one called nominal. If there's no rating specified on a filter assembly or a filter cartridge, usually it's the absolute rating that they give you. They all have slightly different terms regarding the degree of filtration that they have. But what the absolute rating is the diameter in microns of the largest spherical particle that will pass through a filter under a certain test condition, an indication of the largest opening in the element. So realize that there are particle sizes. And again, if we're talking about the absolute rating, it's the largest, or I should say an indication of the largest opening that we have in that filtering element that will trap the particle. There's another rating that's called a mean rating, and it means average. It's a measurement of the average size of the opening in the element, and not all manufacturers provide that in literature. And again, there's another rating called nominal. It says the size of smallest particles of which 90% will be trapped in an element at each pass through the element. But again, if there's no rating that's specified, usually what's inferred is usually the absolute rating. It's the largest opening in the element itself for trapping particles. There's also some other terminology too regarding filters and elements. A flow rating versus pressure. Understand that the filter offers a restriction in the hydraulic circuit, and it causes generally a drop in pressure across it. So sometimes they're rated by manufacturers in gallons per minute of drop at a specified pressure. Also too, if you were to measure the difference in pressure across an element, in other words, the inside of an element versus outside, that would be defined as differential pressure. Sometimes they have a differential pressure rating for the element, what is designed to normally see. In addition to that, they may also have a collapse pressure that they specify in an element. And understand it would be the exceeding value of differential pressure, so that you have so much pressure on the outside of an element compared with what's inside that you can actually collapse the element. But, anyway, there's a lot to filtrate.
Is it greater on the outside as it is on the inside?
Generally, it's going to be greater. There'll always be a higher pressure found on the entrance way of a filtering element versus what's inside, because the filter itself provides a degree of restriction. As contaminants built up, the difference in pressure will also become greater. So because again, you've got a higher pressure on the outside versus what you have on the inside of the element. We can find filters in a whole bunch of locations in a hydraulic system. They can be installed in the pressure manifold. This would be a location anywhere after a pump. So any place in the pressure manifold. They could be also found in a return manifold. This would be after a component headed back toward the reservoir. So you can find it in the return manifold. We also find filters that are installed in a pump case drain line. And again, the filters, provide for filtering the fluid before it goes back to the reservoir as part of a cooling loop. Also understand too that you may have integral filters inside of a reservoir, just like we talked about before break. You may find a filter assembly or filter installed inside of that reservoir. And in many actuators, particularly flight control actuators like power control units, you may find what are called last chance filters. These are usually microfine type of filtering elements, wafer type filters that are really only replaced in the course of overhaul of a power control unit or an actuator. They're usually not serviced as part of regular maintenance of an aircraft operations. But when a component has reached a certain life cycle, a particular hydraulic power control unit, usually it goes to a certified repair station, and those filtering elements are replaced there rather than in the field. It's done almost like in a clean room environment. So these are where common locations where filters might be found. One thing that you have to understand too is how we kind of size the particles in terms of filtration for a filter. We use the metric system for gauging filtration, and we use a divisible value in the metric system for sizing called a micron. A micron is a millionth of a meter. So here's a comparison scale of what we have for a human hair. The diameter of that human hair is roughly 100 microns in diameter. And a particle, or at least a micron, would be 1/1,000,000th of 1 meter. So what we're talking about for particle size trap for the absolute rating for a lot of filters for older aircraft, usually about to the 10 micron size. So we're able to trap particles down to about 10 microns in value. Also know too, we can have a US or an imperial equivalent in terms of sizing. So again, 25,400 microns is equal to an inch. But a far easier way of describing what a micron is just to use the metric system. And what I'd like you to remember is a micron is a millionth of 1 meter. Okay, so here's another chart to kind of show you what we have for sizing. And again, relative sizes only, but down at the bottom you can see the size of bacteria, cocci. It's about 2 microns in size. This kind of explains its ability to traverse the human body with ease because it's so small. Red blood cells have got a micronic size equivalent of about 8 microns. White blood cells about 25. And what you can see with the naked eye without any form of magnification would be somewhere around 40 microns. And that would be with new eyes, not certainly mine. So in any event, again, generally hard to see anything smaller than about 40 microns without some type of assistive aid. We also have things in hydraulic systems that are not technically considered to be filters, but they're more in line with what we would call strainers. They're usually made out of mesh types of screening elements. And we have mesh sizing that goes all the way from about 50 mesh to about 325 mesh. The higher the mesh number that you have means a finer degree of filtration. But what I can tell you about the mesh sizing, even the finest of mesh that can be manufactured, like 325 mesh, it's not capable of trapping down particle sizes down to 10 microns. It's usually something quite coarser. 50 mesh, of course, is the coarsest of the mesh sizing. But anyway, this kind of shows you relative sizing. This is only a cursory check of hydraulic fluid for solid contaminants. And again, I say cursory because, again, if the particle sizes are beneath the threshold of visibility, it's not going to be detectable. And it doesn't matter how many of them there are in it. Generally speaking, if the particle sizes are underneath 40 microns, it's not going to be visible. What you might be able to detect with a sample of hydraulic fluid, you might be able to detect maybe thermal stress. You might be able to discover discoloration of the fluid, maybe from foreign fluid contamination, maybe even the presence of water. But again, remember, if we're talking about solid contaminants and hydraulic systems, if the particle sizes are beneath, say, 40 microns, this is not going to help too much. Okay, so just a cursory check of fluid by visual means. Here's a linear equivalent table and a chart that you can kind of look at. If we look at a micron, and again, this is the abbreviation for a micron, it's 1 times 10 to the minus 6 meters, which is really 1/millionth of a meter. And again, for a lot of the modern or more modern aircraft, we're trying to trap particle sizes going down to about 10 microns. That would provide a meaningful degree of contamination control for the bulk of the aircraft that are currently produced. In terms of sieve sizing for a mesh screen, we have things that go from a roughly 50 mesh to about 325 or so. And what we would find for the absolute rating for something in 325 mesh would be about the equivalent of about 44 microns. So they'll trap something maybe a little bit bigger than was visible by the naked eye, but that's all that we're able to actually create by man-made materials. So at least for a screen anyway. Also kind of a chart that shows you the importance of particle control in aircraft. The sliders that we have in a lot of the power control valves and power control units, this would be the distance between pistons and the cylinder wall. Sometimes it's very small, and it might be in the vicinity of maybe, I don't know, 5 microns or so, 6 microns. But again, we have to be able to control contamination to a tolerable level. So again, we want to certainly be able to prevent blockage or at least wear and tear in those component parts by controlling particle size as much as possible. And you can see by mesh filters, something like this, we're maybe about, 30 microns, 40 microns in size. In this case, 15 microns. Wire mesh filters, this one quite large, about 25 microns in size, and 40 microns this would be visible by the naked eye. Okay. A lot of different types of filter elements and mesh screens that might be used for filtration purposes. Some of them we've already talked about. For example, in a filler neck of a reservoir for servicing, you might find a finger strainer that looks like this. And again, it prevents gross contamination from getting into the hydraulic fluid in the reservoir. More commonly, for a lot of aircraft, we find cylindrical filter elements, kind of like what you'd find in an automotive type application for automotive engine oil, but it's a cartridge. In this case, it's just a paper element that's been capped on both ends of it. You might find also maybe another type of filter we'll talk about later, called a sintered element, but again, not too common for hydraulics. You might find woven mesh or woven material that's used for filtering purposes as well. But probably the most common for aircraft hydraulic fluid would be something like this. This fits into a filter bowl with a head assembly, and it's replaceable usually. Screens, again, on aircraft, usually mesh screens, don't filter down to the micronic level necessary to control filtration. But again, if it's used in some aircraft, it's used usually for gross contamination control. This is a particular type of filter that you might want to have a little bit of history on. It's called a Kuno filter, and it's actually a trade name, just like saying Pepsi or Coca-Cola. And the company is still in business, but in the 1930s, 1940s, it was a quite popular filter for hydraulic systems for filtration. It's not considered to be adequate today for modern aircraft because the degree of contamination control is too coarse. But there were a couple of different screen equivalent sizes that were used for Kuno filters. One of them would go down to about 70 mesh in sizing, and the other one is about 170 mesh. Again, a little bit of a different. The method of filtration on a Kuno filter is quite different than most other types of filters. You'll notice from the head of the filter assembly, there's a T-handle that protrudes from the top that goes down into the bowl of the filter. If you take a look and see exactly what that represents, it represents a core of a type of filter. What you have that inside of the filter is really a series of discs and spacers that are stacked one on top of another. And the hydraulic fluid is able to get into the bowl of the filter and circulate, and if there are contaminants present, the particles are trapped between the spacers, the space that you have between the discs. And what controls the degree of filtration is really the distance that you have between the discs that's kind of regulated by these spacers. So you have a series of disc spacer, disc spacer, disc spacer, disc spacer, and any debris that happens to be floating in the fluid kind of gets caught between the discs. And again, that's kind of determined by the thickness of the spacers. There used to be an FAA test question that would ask you what controls the degree of filtration in one of these filters. And what I want you to remember is it's really the thickness of those spacers that really controls it. So we can make them down to kind of, razor fine, but you'll never be able to man make them, or at least control them to a micronic level. This type of filter was common in World War II for some aircraft where we had to control filtration, but again, those aircraft at that point in time anyway were more tolerant of contamination, and it was good enough. The way that the filter is cleaned is kind of interesting too. You'll notice that they've got another rod that is positioned next to the central core spindle rod, and that rod contains cleaning blades. When you turn the T-handle, what you're doing is you're wiping these cleaner blades between the discs in the area where the spacers are at. What that does is it dislodges the debris so that it falls down to the bottom of the bowl. Ultimately, what you'll do at some later date is open the drain plug up, and then the sediment that has been collected down at the bottom after it's been knocked off from between the discs can be drained out at that time. But maybe as part of a pre-flight, they might turn the T-handle a couple of times, and then off you go. That's it. It's enough. And then maybe at the 50-hour or 100-hour inspection, we'll open the drain plug up, and whatever captured debris we have, we'll get rid of it at that time. We have one of these filters in the shop that came from an early gas turbine engine, but not one specifically for hydraulic fluid. That one was filtering turbine engine oil, or turbine engine oil. Also, too, when you take Lonnie Bosselman's class, he may talk to you maybe a little bit about oil filters and the filtration that's progressed through the years on engine oil. There were some radial aircraft engines that had a Kuno-type filtering element or filter mounted on the nose case of the aircraft engine that turned through reduction gearing in order to filter engine oil. So again, the T-handle in that case was really replaced by reduction gearing that provided for cleaning the engine oil of the aircraft when the engine was in operation. But again, considered to be kind of too coarse for hydraulic purposes today. Oh, by the way, too, the method of filtration that's associated with Kuno filters, remember the term edge filtration. So when we're talking about this type of filter, it filters not by surface filtration, it filters by edge filtration. The debris is actually trapped between the edges of the discs, and that's how it works. The company is still in existence, but now they've kind of morphed into a company that's more associated with water filtration, and they've kind of divested themselves of aircraft filters. But again, an old-timey type of filter. There's another type of filtering element that's called a sintered element. And again, not too common for hydraulics, but again, for other media that you're trying to filter, you might find it. These type of elements are used in older automobile fuel systems. It's sometimes a carburetor filter element. And again, they're more often made out of a material that can be molded, or it has malleability that's in a particle form initially. So what they do to make a sintered element, they take a malleable material like bronze, and then they force it into a mold. And then when they take it out of the mold, the malleability of the material kind of makes it cling to itself, but it leaves a great deal of porosity that whatever media you're trying to filter will pass through it. These filters, again, don't really filter down to the micronic level, but they do provide adequate filtration for older automobiles. Years ago, I had an old Mercury Comet. It had a 302 V8 engine in it, and the thing was fast. However, it stopped one day, and lo and behold, I had picked up some contaminated gasoline, and I discovered after a little bit of investigation that the centered element at the carburetor was blocked. So I replaced it, and that was it. You know, that was the end of the fix. That took it back to running again. There are other materials that can be centered as well. They've now learned, or at least it's now possible to center stainless steel. But again, it starts out as a particle or a flake type of material that can be molded into a shape that provides for a degree of filtration. But again, probably a better type of filtering element for gasoline than other things. Another application for centered elements, if you look at a lot of pneumatic regulators, the regulator inlet on a lot of gas regulators has a centered element in it as well. So if you're using an oxyacetylene rig or you're servicing an accumulator from a gas cylinder, the regulator section of that goes onto the gas cylinder sometimes has a centered element in it. This is what we might find for an aircraft. We might find a filter assembly. You've got a head, a bowl, and inside of it you've got a filtering element that is probably replaceable. Notice that there's an arrow that's on the filter head assembly. Many of the head assemblies, they have a bypass valve that's installed. The bypass valve is there in the event that the filter becomes clogged, and if the difference in pressure becomes excessive beyond what the filter element is supposed to see, the bypass valve will open and allow unfiltered fluid to pass through the head assembly. But again, there's a bypass valve in this particular head. Here's one. They show you a cross-section in the old airframe book of the head assembly, the bowl, and also the filter element. So you can see kind of what happens. The hydraulic fluid comes in, it circulates in the bowl, and then it permeates through the filter element, and then it's cleaned, and then the fluid comes out. There's a certain amount of difference in pressure across the element in normal filtration. However, if debris begins to build up on the outside of the element, that means that there'll be a greater difference in pressure across the wall of the element. And at that time, the bypass valve will open and allow the fluid to escape through the head assembly, bypassing the element itself. The theory being that dirty fluid is better than no fluid at all. Now the picture shows a bypass relief valve opening at about 50 pounds per square inch differential, but understand that that really is just a baseline. It could be whatever the airframe manufacturer, whatever the system kind of demands. If the normal filtration perhaps has a difference in pressure of maybe 50 pounds per square inch differential, maybe the bypass valve may open it up at 75 psid or 100 psid. But again, this is just a representative example. We would know in this case that the filter is, the element itself is certainly in normal flow, has a normal difference in pressure of less than 50. And the bypass valve would open at greater than 50. Most of the filters that the FAA will test you on as part of the written examination, they're talking about a specially treated type of cellulose paper. It's actually impregnated with a resin that is a replaceable type of element. And let me just kind of cut right to the chase and show you. They're talking about something that looks like this. These elements are common in aircraft of the 1940s, 50s, 60s, 70s, up through the 80s. And again, they provide a degree of filtration down to about 10 microns or so. There's about four different sizes of them that are used in hydraulic systems. And I looked up the spec on this particular one. If you want to look it up on everyspec.com, you can, but they will trap particle sizes down to about 10 microns. What you should know about these elements, they are normally replaced rather than cleaned. To attempt to clean them usually means that the paper element will disintegrate if you try to backflush it or ultrasonically clean it. The reason that it has pleats, folds, or convolutions in the paper is to add additional surface area for more filtration. We could simply have just wrapped the filtering element with paper as a cylinder. However, it wouldn't provide nearly as much surface area if you had folds or convolutions or pleats in the paper. So that's why you see it here. These elements are generally designed to be replaced when they're contaminated. A spring is located on the inside of the element, and the spring prevents collapse of the element from excessive differential pressure. There's a more modern type of element that's found in aircraft today, and it kind of looks like this. Some of these elements are cleanable either by back flushing or ultrasonic means, and some of them have to be replaced. Usually you'll have to look on the service manual or maybe on the filter itself to see how that, what particular type of remediation you have to do. But again, some of them, you replace them, you can clean. Most of these elements are not made out of paper. They're made out of maybe a stainless steel type of mesh device, and some of these things will filter down to 5 microns. So again, take a look to see specifically what type of element that you're replacing or what you're actually doing when you have to service an element. So again, some of them are cleanable, some of them are not. You'll have to look in a service manual for some guidance on them. Okay. And what else can I tell you? They're pretty simple. The way that they work by surface filtration. If you look at the bowl and the head assembly, you can kind of figure out what's happening. The inlet allows fluid to come in and circulate in the bowl, and then it goes through the element, and then ultimately it comes out the outlet. And many of the filter assemblies, they do have a bypass valve. If the difference in pressure across the element becomes excessive, maybe from contamination, well, the bypass valve will open and allows unfiltered fluid to bypass the element. Many of these filter head assemblies also incorporate a differential pressure indicator. They're usually mechanically operated, and they're held seated by a magnetic circuit. I've got both of the kits that we have out in the shop that have the filter parts of the filter checkout in them have a differential pressure indicator either mounted in the head or separately. And it's kind of interesting to see how those devices actually work. They work by sensing the fluid at the inlet side of the element and at the outside of it. And let me show you a better picture to kind of show you what's happening with these things. Here's a picture of a DPI or a differential pressure indicator that's mounted on a filter head. In normal operation, one side of the poppet or the piston that's in the indicator just sees pressure on top of it, and it also sees fluid that's going to be on the outlet side of the element as well. So you have fluid that's entering on top here, and then also there's fluid that's also on this side of the element. These two pieces of the DPI are held seated by a magnetic circuit. However, when there's a big difference in pressure, there's more pressure on one side of this particular poppet or piston, it breaks the magnetic circuit and will allow the pin on the outside of it to protrude. So you can tell if you've got a difference in pressure. You don't know whether or not the difference in pressure problem is the result of contamination, but you do know that contamination causes difference in pressure. So you have to investigate a little bit if the pin actually trips. You should be aware too that there are things that will cause erroneous indication where the pin trips, and it's not due necessarily to contamination on the walls of the filter. If the fluid is cold, that means that it's viscous. It means that you're going to have probably a higher pressure on the outside of the element than on the inside core of the element. So when you start the aircraft pump, you're pushing thick viscous fluid, and again, it causes enough of a difference in pressure to possibly indicate a false, provide for a false indication of a difference of tripping. So it may trip. Another thing that could cause maybe a potential false indication would be a sharp bounce that breaks the magnetic circuit, or maybe even a pressure spike. Maybe the regulation of system pressure isn't all that great, and you've got a problem in pressure regulation. Either the pressure regulator has failed or the compensator inside of a pump has failed, and it'll cause an erroneous indication too. So for that reason, in a lot of service manuals, they provide for maintenance to make one reset attempt. So, okay, you attempt to reset the indicator and it does not reseat after a reasonable period of time. That may mean that, in fact, yes, the element is contaminated. You're going to have to replace the element. Another thing you should know, too, is there's kind of a hierarchy in difference in pressure. Obviously, the lowest difference in pressure is a normally operating filter. So whatever pressure you have across the walls of the filter is whatever you've got. The next level of difference in pressure would be the point at which the indicator would trip. it will be at a higher difference in pressure because, again, as debris builds up on the outside of the filter, you're going to have a higher difference in pressure. The last point in difference in pressure would be the point at which the bypass valve opens, the relief valve opens. So the indicator is between the two. So you've got normal filtration producing a normal amount of difference in pressure, and then the bypass valve opening, which would have to require the greatest amount of difference in pressure. So the indicators are really termed, they're termed as impending indicators. It's a warning. If the indicator trips, it means that the bypass valve is not open, but you have to perform some type of investigation that, in order to determine actually what the cause of that is. So it's a point beneath the relief valve of the bypass valve actually opening. There's really no other method that I can think of that they use in hydraulic systems in order to indicate impending bypass or filters that are potentially clogged with debris. But that's what we have. So that's it. Some manufacturers of these differential indicators have a plastic ring that's inserted around the pin itself. It contracts by nature in cold weather, and it prevents erroneous indication from cold fluid, but some of them don't. As I understand it too, some of these indicators are mounted in the bowl, or the reset is mounted in the bowl of the filter, which kind of forces a technician in order to remove the bowl to inspect the element in order to reset the filter. I don't know what to tell you to do in that case, but in any event, not all of them are mounted in the filter head. But that's what I can tell you about them. Here it kind of shows you the hierarchy of what you have with a filter in operation. So again, filter, in this case, whatever filter difference in pressure we have, it's certainly beneath 70 psid, but you might have 50 pounds per square inch normal difference in pressure across the element. This particular indicator will trip at 70 plus or minus 10 pounds per square inch differential, and then the bypass valve opens at, looks like about 100 pounds per square inch differential. Also too, what you might notice on a lot of the filter assemblies, the bowl provides for an automatic shutoff once you attempt to replace the element. There's a poppet that's installed inside of the head assembly that blocks fluid flow in the head should you remove the bowl. This does really a couple of things. It prevents contamination from getting into the circuit as you're replacing the element, and also prevents you from losing a lot of fluid from the line. When elements are replaced too, follow the information that's in the service manual. In some cases, they want you to fill the bowl filled with clean fluid. So again, it avoids having the potential for a lot of air being trapped in the circuit. So again, follow the information that's in the service manual for servicing. Let's see what else I can tell you. This is kind of interesting. This was discovered, it's from an Australian service bulletin written up, kind of like what the FAA does, but you'll notice that the head assembly on that filter has been misinstalled. The filter element will work correctly. However, if the element becomes blocked, the bypass valve will not function normally because it's contained inside of the head. So again, this was kind of discovered during an inspection. Somebody had put the head assembly of that filter in backwards. Something else that you might want to remember too, not all filter assemblies have a bypass valve by the same logic that I told you that many of them do. The logic is if a bypass valve is present, dirty fluid is better than no fluid at all. Okay, everybody gets that. But sometimes too, the consequence of contamination is so great that we can't afford any contaminants passing by the element. So we just don't have a bypass valve. Here's a good example from one of the legacy aircrafts, a Boeing 727. In the Boeing 727, they have filters in the return circuit, they have filters in the pressure circuit, and they also have a filter in what's called the case drain. The case drain, it provides for a cooling loop of the pump. In many of the aircraft, what you have is one reservoir that furnishes fluid to multiple pumps. They use a non-bypass type of filter assembly in that cooling loop for the cased drain. The purpose of the filter is what they tell you in the Boeing manual. It says, provided to detect incipient failures of the hydraulic pump and therefore prevent contamination of the hydraulic reservoir and possible damage to the remaining hydraulic pump. So in this case, the consequence would be damaging the other pumps that are in the same attached to the same reservoir. So what you would periodically do is you would examine the filtering element, and then if it was noted that debris was found in the element, it would be kind of an indication that the pump is failing. So you would have remediation, of course, would be to repair or replace the pump. But if we had installed a bypass valve in that filter assembly, you would have polluted the reservoir that would have contaminated the remaining pump. Do you all see that logic? Good. Okay. So again, just understand that not all filters have bypass valves. Some of them do, some of them don't. May have an indicator, but not all of them have a bypass valve.
So if the filter plugs completely though, that's out of, that's.
And you know what? The consequence of that is that the pump doesn't see cooling. That's it. So, but again, the more severe problem is that you've now got a pump that is failing, and if you allow the fluid to bypass, it now pollutes the entire reservoir, which contaminates both of the pumps that come off of that reservoir. Okay. Okay, so that's it. What else can I tell you about these elements? Oh, there's also some legacy aircraft out there. This is the return filter assembly. It may contain multiple elements in it. And understand that because the filter element provides for a restriction in the circuit, you may find different types of elements that provide different degrees of filtration. When there's a huge flow of fluid that is returning back to the reservoir, they provide a coarser element or a pathway for a large slug of fluid to pass back through that kind of bypasses the primary filter element. So again, by design of that aircraft hydraulic system, they had to engineer a method to prevent backup of fluid in the return manifold. So when a lot of fluid is returning back to the reservoir, they just provide an additional element that's in that provides a pathway for fluid to go back back to the reservoir. And what else I can tell you? Oh, let's see. Anything else that's important? For large commercial aircraft, all of the filters are housed together in modules. So again, you might find maybe a case drain filter in one of the bowls. You might find a pressure filter, and you might find also a return filter that's installed as well, all in a manifold. This makes servicing much easier. So if you're charged with having to as a course of action replace elements, well, this is how it makes my life much easier. Rather than to go to individual filters located at different points in the circuit, they've housed all of the filters together at one point. This shows you a module of what you'd find, or a cutaway pictorial of what you'd find for a module. So you might find temperature switches that indicate they're part of it. And again, if the temperature in this case gets better than 250, it provides a warning indication on ICAS for Boeing aircraft. Also, they've got a pressure switch that may indicate maybe a potential difference in pressure that you might have, and a quick or a ground service disconnect fitting that's also attached to the filter module. And again, okay. Picture from your airframe book. I don't know what aircraft that came from, but again, multiple filters held within a module, and then a differential pressure indicator that they have mounted in the head assembly. This is 757 return filter, and again, kind of common. I talked to you already about that. And again, sometimes you've got a diaphragm, or they've got this kind of strange device in some of the head assemblies. As you unscrew the bowl, it closes off the head assembly, so it prevents leakage and contamination getting in. And delta P, I don't know, this came out of the new airframe book. So again, I think they're talking about the contracting ring in this case, or a thermal lockout. Also too, not only do we have to protect hydraulic systems from contamination, but pneumatic systems as well. A lot of gyro instruments will suffer greatly if we don't control the airflow through the gyro case. The gimbals will be damaged by scoring from abrasive material, or at least their pivots will, and then sometimes the gyros will ultimately end up processing. So installed in a lot of pneumatic gyro instruments, we'll find either inline filters or we'll find an inlet filter. These are used in both pressure systems for gyros and also vacuum systems for gyros. A lot of the Cessna and Piper aircraft pull air through the instrument case, and what we'll do is we'll have a filter installed at the inlet as we pull the air through the instrument case, and then the air exits really from the pump and then overboard. In the case of Beechcraft aircraft, they sometimes have a canister type element that's installed in the pressure line, and again, it performs the same function. It filters the airflow before it gets into the case, and to protect the gyro. By the way, too, the gyro instruments that we're concerned about, you know this from general, we're not talking about pitot-static instruments. What instruments are normally gyro powered? What would that be?
HSI.
Yeah, the artificial horizon and the directional gyro. Okay, those are the two common instruments that we have that are powered pneumatically by pneumatic air pressure from a vane pump. But anyway, the fittings that you have installed on those filter assemblies, they're beaded connections. And you can see they've got a clamp that kind of slides around the tubing. And you've got a raised area on the piece of tubing that we call a bead. It's a low pressure connection, but that's common on a lot of these type of filters. Most of the filters are replaced, they're not clean. They will filter down to a great degree of filtration, in this case, 0.3 of 1 micron. So it's, but again, understand too, you are filtering air, you're not filtering hydraulic fluid. And they're replaced maybe every 2, 3, 500 hours of operation. Okay. Lastly, what I want to talk to you about are last chance filters. Last chance filters are usually not seen by maintenance technicians. They're usually part of a servo valve or a servo actuator, where what we're trying to do is we're trying to prevent the particles from ultimately damaging an actuator. So that's why they're called last chance filters. Many of these things can also go down to extremely low levels of filtration, 5 microns or lower, but they're not replaced in the course of normal maintenance. They're usually replaced as a result of sending a servo valve into a repair facility, where the repair facility completely dismantles the actuator and does a rebuild, or at least returns it to serviceable standards. So a lot of them look like this. They're micron type wafers that cover orifice openings, but they're last chance filters. Contamination sources for hydraulic fluid. Understand that the type of contaminants that we're trying to trap from hydraulic fluid have one thing in common. They're generally all solids. It's true that we can have contamination from foreign liquids and from vapors from gases, but the elements that we've talked about tonight are not capable of trapping that type of contamination. The only type of contamination that these elements will trap are solids. Well, what kind of solids might we find? We might find something like metallics, which would be either ferrous or non-ferrous metals. You might find maybe dirt or lint from a rag, or you might find bits of leaves, anything that might be found that's metallic in nature. Sometimes even components, when they're manufactured from a casting process. Sometimes a bit of sand from the casting finds its way into the hydraulic fluid as a result of a flaw. So again, very abrasive and again a solid contaminant. But what we try to do when we service hydraulic systems, we try not to negligently damage the fluid by poor maintenance practices. We don't use tape and improvised closures in hydraulic systems. We have appropriate plugs and caps that we use when components have to be replaced. So again, the last thing you want to do is stuff a filthy, dirty rag into an opening as you remove a component, and you want to properly prevent the fluid from being contaminated by something else. A lot of the components, again, have platings or finishes that can wear, and that can provide also a source of contamination and adverse conditions. One of our students came back from Afghanistan with a vial. I still have it someplace, and it contained what looked like talcum powder. And he came back from Afghanistan, and I said, "What's that?" And he said, "That's sand." And I said, "It's as fine as talc." And he said, "Yeah, it is." And he says, "This was the major reason why we had so much trouble in Afghanistan with the equipment, was because of contamination with this stuff. It's so fine, it gets on everything, and it's almost impossible to remove." So again, sometimes the conditions of the aircraft are in kind of dictate what has to be done. Foreign fluids can sometimes lead to solid contaminants, but again, the liquids themselves really won't be trapped. If there's some type of commingling of fluid that allows for solidification, well, I guess that could be. Another cause of solid contamination would be sludge. When fluids are overheated and overtemp, they will oxidize, and the oxidation produces a solid contaminant that we call sludge. And that's a solid that will be trapped in the elements as well. So again, sometimes it's not the direct result of a solid, it's the operation of the piece of equipment that kind of leads to a solid contaminant being formed. But anyway, that's what we're talking about. And again, gases. I think you realize when we were talking about Skydrol in particular, phosphate ester-based fluids, those fluids are prone to contamination from chlorine or chlorine-based products. So if you inadvertently, negligently wipe down a piece of equipment or a component with some type of chlorinated solvent, you are damaging or potentially damaging the fluid by doing that. So just understand that. Water too. Sometimes people forget to put the cap back on a reservoir, and of course it rains or condensation builds up inside of the fluid from atmospheric air. Well, water can be entrained in the fluid, so not good. This is the check for contamination of phosphate ester-based fluids. They use a halogen detector to detect for presence of chlorine. And it's the same type of detector that they use for using in air conditioning systems for halogenated hydrocarbons like Freon. But there's a limit that's specified in some manuals. As a matter of fact, if you look at the literature I showed you last week or so on from the Skydrol people, they showed a table of what would be considered to be the acceptable limits of contamination for chlorine. Well, again, a tolerable level, but certainly no more than that. If the level of chlorine becomes excessive, it leads to the formation of an acidic compound in the hydraulic fluid. So again, what they use is a halogen detector in order to check for that. Fluid sampling. There's a standard for fluid sampling. I can't remember what the number is or the mil-spec number is for it. But if you look it up, what it tells you is when we sample hydraulic fluid, it must provide for the worst case of a particulate indication. So we wouldn't sample from an area that's not capable of indicating the worst possible condition of the fluid. You want to sample from an area that will give you the worst possible case. The location must not be in a sediment area of the filter bowl either. So again, you don't want to erroneously indicate something that may be wrong. You want to have a realistic indication of contamination. Usually when we sample hydraulic fluid, circulation of fluid is required prior to taking a sample. Usually they circulate for 5 minutes and then purge a small amount and then capture a small amount of it for sampling. The point for sampling has to have an opening or an orifice size that will allow for a 500 micron particulate to escape. So again, one of the conditions for a sampling valve. And again, the sampling valve, it has to be designed not to introduce contaminants. A lot of the sampling valves, ooh, boy, didn't mean to do that. A lot of the sampling valves look like this. They're plunger actuated types of valves, and they've got a mil-spec number, but again, once you open the valve up or you push the button, a quantity of fluid will come out of it, and you capture a portion of it in order to verify its cleanliness. That's it. Now, let me talk to you a little bit about checking fluid for contamination. This is the picture that they used to show in the airframe book, and years ago I kind of wondered what the hell they were doing with this thing. But for people that are in the military, you might recognize this type of test for contamination. It's an early version of a filter patch test kit that's used for checking contamination in fluid. The military has kind of gone away from this, so the same thing with commercial operators, because it's somewhat subjective in the results that you get when you use this type of test. What they're doing is they're putting a filter element on top of a vacuum source and then subjecting a cup with fluid into it on top of the filter and pulling it through into the crucible. So they've got kind of a vacuum that's pulling it through. Then they wash the filter element of any debris that might have been accumulated, and then they take the filter out and then they examine it by comparing it against some test standards. And this is an early version of the kind of kit. And there's a later version from a military manual, and this is what a modern kit kind of looks like today. But again, what you're doing is you're putting a sample of fluid into the cup up the top with a filter element in it, producing a vacuum with this little hand-operated pump and pulling the fluid through the filter, and then eventually we'll take the filter out of it and take a look and put it into a test standard booklet and kind of compare it. What you see when you look at the little test standard, you can look at the colors. There's what they call a gray standard and a tan standard for contamination control. The tan standard is used for detection of ferrous metals, chlorine, and silica. The darker it gets, it somewhat indicates the degree of contamination by those materials. The gray standard is used for almost everything else, including water. So if it's darker than the standard where it's spotty, it usually indicates the presence of water. Same thing with it's hazy as well, but it's somewhat subjective. If it's handled inappropriately when you're doing the test, it leads to subjective results when you compare it against the standard. The kit is expensive. I priced one of these things out over 10 years ago. A commercial kit from Millipore ran about $1,500, and I couldn't get the dean to buy into it, so she said no. But it would have been a nice thing to kind of have to take a fluid sample with anyway to use it. If you want to use it for checking, using a patch test kit for phosphate ester-based fluids, the seals and gaskets that are inside of the testing unit have to be replaced with something that's compatible with phosphate ester-based fluids. But anyway, it's a filter patch test kit. And a more accurate method of determining solid contamination, this is done at a facility where we can have a more accurate measurement of solid contaminants, but by using a particle counter. What they do is they sample it, goes into the particle counter, and then a high intensity light is used in order to produce a shadow that reflects off of the particles of fluid that are flowing through a tube. And then we can get an accurate particle count, not only in number, but in relative sizing, that we can discern actually how much contamination exists. If you want to take a look at the NAVAIR manual that we have in the AVIM library, they give a very good descriptor about how these particle counters actually work. But it's probably a better method of determining solid contamination rather than using a filter test kit or a patch test kit for the field. This is a contamination standard that was used by the military years ago for particle count. And what they do is they rate particle count two different ways. They rate particle count in terms of size and number. And they've got two columns that are kind of important. They have a class 5 and they have a class 3. And it says here, down at the bottom, class 5 is the maximum acceptable contamination level for hydraulic systems in naval aircraft. Fluid delivered by service equipment under test or being used by service, but class 3 or cleaner. So if we're using ground service equipment, the fluid when it's checked has got to be at least of a class 3 in cleanliness. But for aircraft, again, this is 5. you'll notice that the chart is kind of arranged in particle sizes and size on one side, and then going across, it's the number of particles that you have. So you can break the class either by having more particles than for a particular column, or the sizes are greater than would be tolerated by a particular column. So again, it's based on really two things. They're using 100 milliliters of fluid for the sample, but again, the total number of particles in that sample, if we're talking about class 5, can't be any greater than 112,000 or so. And if we're talking about particles that are greater than 100 microns, let's say there's better than 41 of them, well, it can't be class 5. Same thing if again on the particle sizes or the numbers of particles exceeded maybe 100,000 of particle sizes from 5 to 10 microns, it forces it to be unacceptable. So again, it's based not only on size, but it's based on number as well. The standard that was used for commercial aircraft in the past was this. It was an ISO standard developed in 1964. And it was a standard, again, based on particle size and number. But again, for commercial aircraft, they used 6 and 8. They used 8 for the aircraft and 6 for ground servicing equipment. Same type of contamination control that they kind of use for military aircraft. Later on, as the aircraft developed and we had to have finer degrees of filtration, a new standard evolved from it. It's an aerospace standard in 1988, and it has a finer, how can I put it? It has a more defined level of contamination control than the previous standard. But you can see it goes down to less than or greater than 4 microns, 6 microns, 14 microns, 21 on up. And also the numbers have been reduced in size to give you a tighter tolerance in contamination control. Even in non-aerospace applications, you find something like this. It's a different ISO chart or a different ISO standard. And they use it for things like industrial earth-moving equipment and things that aren't aerospace related. But it performs kind of the same idea. It provides some meaningful information regarding the cleanliness of hydraulic fluid by particles, the number of particles, and their relative size. This is the last thing that we want to do in aircraft. We don't want to throw the fluid out. But sometimes if the fluid is so contaminated, this is really the only thing that we can do, particularly if it's been altered in its chemical nature. If it's been over-temped or it's been polluted with foreign fluids where it's not just solid contaminants. It's extremely expensive to have to do a complete fluid change in the aircraft. The fluid is considered to be a condition item aboard the aircraft. In other words, it has to have a tolerable level of contamination control, and that's it. So again, you have to be very careful when you service the reservoir to know what fluid is used in servicing and not unnecessarily contaminate the circuit by the use of improper cleaning materials or poor servicing technique. So again, you have to be very careful. The military recirculates a lot of fluid, but again, they have an operating environment where they have to. In order to maintain the aircraft in an airworthy status, they have what would be kind of equivalent to dialysis for the human body. So they recirculate fluid through a purifier in many cases in order to filter to a tighter standard than the aircraft would generally have aboard it for normal filtration. And some of it's kind of complex. It's not too commonly done for commercial aircraft as far as I know, but the military relies heavily on it. And that's what I can tell you. I've got some, if you want to research further into recirculation fluid or purification, there's some Navier manuals that we've got in the AVIM library. You might want to take a look at those as well. Okay. So again, I think I've given you a pretty good overview of reservoirs and filters tonight. What questions do you have? Silence. Okay, I guess you know it. All right. Okay. Out in the shop tonight, I'd like you to have you, if you're working on projects, I want you to stay in